Welcome everybody to our is it spring? Doesn't feel like spring, but spring seminar series. There is food on the back. I suggest take some hot sauce to warm up because it's a very cold day. Our seminar series, I do have that, is just introduce myself. I'm Pavlos Protopappas. I'm the Scientific Program Director for the Institute for Applied Computational Science. And I just want to say a few things about this seminar series. Because we are an interdisciplinary institute, we cover a variety of topics. And during the semester, and people that have been to these seminars before, you know that we cover quite a diverse topics. The main theme usually is computation. So this semester, for example, we're going to start with Brian, and I'll introduce him in a minute. But we have topics that they cover from quasi-randomness, we're going to hear soon, to the whole spectrum of molecules in the universe, OkCupid, finance things, and very other topics. Our full list of seminars is on our website, or will be shortly. So this is the chance to have a nice lunch and hear very interesting talks. We do have, I think, the best lunch in seminars. Okay, so today our speaker is very happy to introduce, an honor to introduce Brian. Brian is actually a CIS associate and has been with IACS for many, many years, since the beginning of times, it feels like. He is a senior writer and a columnist for the American Scientist magazine. He's basically a writer, but he, at the same time, does research or applications or implementation of computational methods, so he knows the material he's writing about, and that's the most interesting thing about him. He writes about computational and mathematical themes for the American Scientist. Is this supposed to be only for American, or can other scientists write? Also, he writes a blog, which I personally love. It's bitplayer.org. Bit like B-I-T. I know my E's are not always understood. It's bitplayer.org. And he used to be an editor for Scientific America in the 70s and 80s. He visited various institutes, like the Berkeley Center for Mathematics, the ICTP, which stands for International Center for Theoretical Physics in Trieste. I'm not sure if he was doing work there, from stories I heard, more sailing and having fun there. He has written 2 books now, or 3 books? I know 2 of them. One is Group Theory in the Bedroom. If you like group theory, and you want to read something interesting before you go to bed. I have read it and I like it. And the other one is this book, Infrastructure, the book of everything for the industrial landscape. You can buy it at Amazon. Sure. Or not. Yeah, yes. It's a good book if you want to buy it. So today, Brian is talking about something that related to a course we teach here, the AM27. And I know this thing not because I'm a random behavior, but because I co-teach that course, is orderly randomness, quasi-random numbers, and Quasi-Monte Carlo. Thank you, Brian.
Thank you, Pavlos. Thanks to everyone for coming out today. The first issue to be addressed here has already come up. It's whether it's quasi or quasi. And I'm afraid that Pavlos and I disagree on this, so but maybe we could take a vote. So I'm going to plunge right in. If I turn the clicker on. Most of what I'm going to be talking about involves this well-known procedure for measuring the area of a complicated pattern. The idea is that you pin it up to the dartboard, you blindfold somebody and hand them a bushel basket full of darts, and you then throw the darts randomly at the dartboard And after it's all over with, and you clean up the spilled blood, you count the number of darts that hit the target versus the total number of darts that were thrown, and this should give you some sort of a measure of the size of that pattern. So we're talking about this in a two-dimensional context where it's really just a toy, but two dimensions are a lot easier to see than 20 or 30. So here we are throwing darts at a square. We can call it a unit square. And in the middle of it is this maple leaf that I grabbed from the tree that shades our porch and scanned it. And the question is, what's the area of that leaf? It wouldn't be that hard to calculate, but this is a procedure for doing so. If we take the number of yellow dots that hit the leaf and divide by the total number of dots, we should get the ratio of the leaf's area to the total area of the unit square. I should, of course, have written something that would actually count the dots that we've just put there, and I could answer the question of what's the area. That'll be for version 2 of the talk, I think. I just didn't get to it. In any event, the point I want to make isn't really quantitative about measuring this particular leaf. It's the procedure that we're interested in. And the question that immediately comes up for me when I look at these experiments is, what does randomness have to do with this? Why do we choose to throw our darts blindfolded? Why is it necessary that we randomize this sampling process? And in point of fact, it's not really necessary. You could take a very regular pattern, run exactly the same experiment, and again, I don't have a counter to present the evidence. You're welcome to count them yourself if you'd like, but I can assure you that the results are not substantially different when you use a totally regular deterministic pattern like this. Incidentally, this was supposed to be an array of dots parallel to the axes, and there's a bug in the program. But I decided it was actually kind of nicer to have them a little bit out of alignment, because in fact it doesn't matter whether they're lined up or otherwise. So the main thing I want to talk about is a kind of intermediate choice between those two extremes of points that are completely orderless and points that have an obvious, immediately apparent crystalline structure. So this is this notion of quasi, not quasi, but quasi-randomness. And so this is just another way of spraying those points over the surface. And it turns out that in some very narrow sense, a pattern like this is probably the best choice. It is superior for certain purposes, and there are all sorts of footnotes that need to be appended here. But it is superior both to the highly ordered sequence of points and the totally random one. So I want to try to explain what these concepts are. And the only one here that's truly random is numbers or choices or phenomena that don't come out of an algorithm. And I think this word urandom is sadly neglected. It's the immediate partner to pseudo-random, where we have essentially fake randomness, things that look as if they've come out of some disordered process, even though in fact they don't. The quasi-random patterns are even less random. They don't look random. They share some properties of the true random numbers and the pseudo-random numbers, but not all. And then, of course, we have non-random things. So the three key concepts that distinguish these various kinds of patterns in numbers for a truly random number, the property that we want to make use of is unpredictability. It is if you imagine a stream of bits, zeros and ones, you want to be able to say that you could look at all of the ones that have appeared so far, and there's no way that you can extract from that historical record anything about what the next bit is going to be, whether it's going to be a 0 or a 1. The consequence of that is that they will also have to be uncorrelated, which means that there's nothing about the particular value of one bit that will tell you about any other one. You can't say if a certain bit is a 1, that increases the probability that another one is a 1. They also have to be unbiased, because if they aren't, if there are, say, more 1s than 0s, then you know immediately something about the next bit. You know that it has a higher probability of being a 1 than a 0. So unpredictability is what we want in random numbers. They have to be uncorrelated and unbiased if we're going to get unpredictability. And where it's worth the bother of using these random numbers is in contexts where you have an adversary, some conscious, intelligent opponent who's able to exploit any weakness in what you've done. Cryptography is possibly the most important example of this, where if your encryption algorithm is predictable, then there's not much point in encrypting with it because someone else is going to be able to undo it. Gambling is another case where casinos are very interested in making sure that that roulette wheel spins randomly, because if there's some pattern in the output, that's something that their adversaries can exploit. In a funny way, proof, mathematical proof, or proof anywhere in the sciences, the process of demonstrating the truth of a proposition can also be seen as a kind of adversarial process, where you have, if perhaps only an imaginary opponent who wants to find a counterexample to whatever it is that you're saying. And it's interesting that randomness has turned up in the process of mathematical proof and become a serious tool for proving propositions. In order to create true randomness, you need some true randomness. You need a source of entropy or disorder, which really comes down to the same thing. And this is one of the very few places in which mathematics and the world of bits seems to be inextricably linked to the physical universe, where there's just no way, without resort to some material process, you can actually create entropy. The world, the universe seems to be full of it. We have no shortage of disorder in, you know, the pile of shoes in the back of your closet or something like that. But there's no known means, and really no conceivable means, of producing something random out of pure thought. The strange thing is that these true random numbers are actually terribly difficult to work with and generally inferior to the fakes. The story that I've long been fond of is about Frank Weldon and Florence Tebb, who were partners in matrimony as well as in science. And they spent their evenings for years rolling dice for science. They were not playing games. They were generating random numbers that would be used in statistical studies. They were biometricians. They were interested in the design of experiments for biology. And I think they had 23,000 dice rolls that they had recorded the outcome of after immense labor. And around 1900, Carl Pearson, the statistician, took a look at these and found that they were terribly biased, that there were too many 5s and 6s. There had been something wrong with the dice. And almost all stories of this kind, even in the late 40s, when the Rand Corporation created this comical book, even the New Yorker had to review it. It was 1,000,000 random digits with 100,000 normal deviates, which I thought was a brilliant job of publishing and titling. Anyway, they went to great trouble, great expense. They had a computer. They created a sort of electronic roulette wheel. And they too ran into the same problem, that the numbers were correlated and biased in ways that they weren't supposed to be. And it turns out, I mean, you can get random bits over the internet. You can buy a little key fob that generates them. But it turns out that the only way to make these things work when they come straight from the hardware is some scheme to whiten them, to remove the biases. This is actually, whoops, didn't mean to do that. Oh, yes, wrong button. This scheme was invented by John von Neumann, and it's still very much in use. If you have a stream of bits that has some randomness in it, but also has a bias, in this case there are more 1s than 0s, if you tried to use use that stream directly, you would get very non-random results. So von Neumann suggested that you take the bits in pairs, and you throw away any pair that are the same, 1, 1 or 0, 0, and then you use each other pair, say 1, 0 becomes a 1 and 0, 1 becomes a 0. This turns out to work pretty well. So with all these hardware devices that produce randomness, it's really surprising to me how treacherous they remain. This is a recent instance. This was in Taiwan, where identity cards were issued that for security purposes generated their own cryptographic key. And every citizen of Taiwan was supposed to carry one of these things. And the security of it was based on generating 2 large prime numbers, 512 bits. And they needed to be random prime numbers, that is, ones that would be hard to guess. So this is one that turned up in an analysis of these cards, and in fact turned up over and over again. And it looks just fine when you look at it like this, but when you write it out in binary, it doesn't look so random. And it turns out it's the first prime after this very round number of well, the two ones that begin it, and then a bunch of zeros. If you start counting there and just go searching for the next prime, this is it. This turned up in several dozen cards. They all generated this same prime number, which means that it's cryptographically useless, because if you have that shared prime, it turns out it's trivial to solve for the cryptographic key. So the lesson here to me is that hardware true random numbers may be the gold standard, but in practice they're almost useless, and the world mostly, for everything except cryptography and gambling and so forth, we're much better off with faking it. And the usual way to do that is with pseudo-random numbers, which in some important sense are totally predictable. If you know the algorithm and you know the one useful piece of information that goes into there, which is called the seed, you can reproduce the whole thing. There's absolutely no uncertainty about it. So they're not unpredictable, but they are supposed to be uncorrelated and unbiased. That is, they look like random numbers. If you run statistical tests on them, if you check the number of ones and zeros, if you look for patterns, they are supposed to have the same patterns that true random numbers do, or the same absence of patterns, I guess, would be a better way to put it. This is more von Neumann. In 1949, I think it was, 51, he was involved in the first effort to make use of random numbers in a computing process. And he put this rather strangely theological twist on the whole business that, and the point is, of course, unassailable. If you have a totally deterministic machine that will follow the same path every time that you set it in motion, then there's no way it's ever going to produce randomness. And you're in a state of sin. Well, von Neumann went forward and sinned. He did a lot of work with that and did not produce very good pseudo-random numbers. But and the sort of counterpoint to that complaint that, that these pseudo-random numbers are just phony, they're not really random, the counterpoint to that is that in the contexts where they are most useful, which involves things like simulating natural processes, where there's no adversary, where you're only up against nature, in those places you don't really need to worry about unpredictability. If you can be uncorrelated and unbiased, that's plenty. It's the absence of the adversary that's important. And this, of course, was Einstein's comment that, in a rather loose translation, that nature is full of complication and sophistication, but there's no malice there. If you try to simulate a gas in a container, if you try to simulate the motions of the atoms, it doesn't really matter whether there is some singular state that would fool your random number generator, because you're not up against an adversary who's going to choose something deliberately to cause you trouble. So the usual way of making these things, I don't know if it's the usual way, the classic way of making them is this linear congruential generator, which is simply a way of producing a permutation of integers. And ideally, you want a permutation that's going to go through the entire cycle. In this case, we generate integers modulo m. If you choose these constants a, b, and m correctly, you're going to get m different integers that are in an order that is not easy to guess unless you know the trick. It's important that they're not really uncorrelated, because after all, if you know the trick, you can predict every one perfectly. Furthermore, because they have a finite cycle length, you can always, even if you don't know what the algorithm is, if you know how long the cycle is, you know that whatever you see at time t, you're going to see exactly the same thing at time t plus m. So these are uncorrelated only if you are willing to play along with the game and not try to go too far with it, not try to generate more than m of them, or even really more than a tiny fraction of m. It turns out they're also not unbiased. They're highly imperfect in curious ways that it has taken decades to really understand. There was an incident in the early 90s when a group doing Monte Carlo simulations of systems in statistical mechanics, basically they were doing random walks. And they kept getting the wrong answer. And everybody who does an experiment with a computer and random numbers, when it goes wrong, you always say, oh darn, the random number generator is failing. There's a bug in that, and that's what's causing the trouble. And I have tried this, I've tried to persuade myself of this on occasion when I got into trouble. It's never true, except that time it was true. That it turned out that the whole problem was that there were tiny biases in the random number generator. It turns out that in that cycle, in that permutation, there's one value missing. 0 turns up one time fewer than any of the other numbers. And there are experiments in which that's enough to ruin your outcome. And as I said, this has really taken a long time to understand. We now have pseudo-random number generators that are really good. And the standard advice is don't roll your own. They're pretty good. So here's one that's really bad. This is the equation that we're running. We're simply iterating. We're taking the current value of the random state, we're multiplying by 41, adding 1, taking that modulo 256. So there are only 256 possible values here. And these, remember, are supposed to be random. So you might want to be on keeping a lookout to see if any patterns should turn up here. Any regularities that you might notice in the distribution of these numbers. Actually, it looks like a measles outbreak. We've all been vaccinated, right?
Are you throwing pairs, Brian? Or are they pairs of numbers?
No. Oh, yes, I'm sorry. Yes, indeed. They are, the coordinates of each point are, each number is used twice. That is, x1, it becomes the x coordinate with x2 as the y coordinate, and then rotating through. Yes. We can do it other ways. You're going to see patterns that are very similar to this in every case. What's going on here is that if you've only got a finite number of numbers, they're going to have to form a pattern of this kind. And if you took a really good random number generator and you went through its entire orbit, the entire cycle of possible values, you would get something very similar. So the key here is that you can't use the whole thing. With this generator that only has 256 values, you'd better stick to 25. So that was pseudo-random numbers, and we now come to quasi-random numbers, where, again, they are unpredictable. This time, though, we're going to give up the quest for uncorrelated numbers. All we're going to ask is that they be unbiased in the sense that if you're looking at them as numbers, there are as many ones as twos as threes, and then you can do the same thing with pairs or triples or whatever. If you're looking at them as points, which is mostly what I'm interested in here, points in space, then you want them to be equitably distributed. You want every region of the plane in the examples I'm giving, or some higher dimensional space. You want every region to have the same likelihood of being chosen. The interesting thing here, which has been known for a long time and only in the past 10 years or so has really been seen as very useful. The interesting thing is that if you give up those other desiderata of unpredictability and lack of correlation, you can actually do better on the unbiased part. That is, you can remove more bias by using numbers that are in fact correlated and predictable. So here we go with quasi-random patterns and more measles. And this, to me, is vaguely mysterious in that this does not, to me, look like it has a more uniform distribution than either the random or especially a simple lattice, a totally regular grid-like pattern. But it turns out if you measure the uniformity, which I'm going to talk about in a moment, this is in fact less biased in a very special sense. What it comes down to is that if you divide up that square into a whole lot of smaller squares or rectangles or other shapes, you'll find closer to equality in terms of the number of dots that fall into each such square. So with the quasi-random numbers, this is totally deterministic. There's not even a seed as there is in the case of the pseudo-random numbers. They don't look random. They have no pretense to randomness, but they can serve the same purpose in many cases. I only put this slide up here so that I could ignore it. I don't know the answer to the question, and I don't actually want to muse philosophically. But it is fair to say that these are interesting questions. There's been lots and lots of hard work trying to figure out what it means for something to be random. One problem being that you can look at a royal flush or a poker hand that has only, has no value whatever. They both have exactly the same probability. They're both just as random. But I am going to set all that aside because we have real meat to deal with in terms of whether or not we can define randomness. We have uses for it. So it turns out that the measurement of uniformity or lack of bias is usually done in terms of something called discrepancy, which is sort of the flip side of the coin. And here's how you go about it, or here's one way to go about it. We can measure discrepancy by drawing a rectangle within our larger rectangle here. We have a unit square from 0, 0 to 1, 1, and we have some smaller embedded rectangle. And the measure of discrepancy is you count the points within the rectangle, you count all the points throughout the entire square. You measure the size, the actual area of this rectangle, and the actual area of the larger square. And the difference between these two ratios is a measure of the discrepancy. If it's basically saying the number of points that fall within any such area should be proportional to the area of that rectangle. So the departure from that ideal is what we measure as discrepancy. And then to measure the discrepancy of the pattern, what you really want to do is find the single rectangle that produces the highest discrepancy. We're going to use the infinity norm here. We look at the worst case. We could also average in some way if you wanted to define a distribution. But the common practice is to use a worst case measure of discrepancy. So you find the particular rectangle that departs farthest from a uniform distribution, that has the greatest excess of points or the greatest efficiency, and that's what defines the discrepancy of the overall pattern. Now, finding, there are infinitely many rectangles that you can draw within a square. It turns out that you don't actually have to deal with an infinitude of them because the ones that count will always have points on the boundary. But nonetheless, if you just count rectangles that are plausible or that are candidates for being the worst possible rectangle, they're like n to the fourth, which is a lot. So the practice that has caught on is something called star discrepancy, where you only consider rectangles that are anchored to one corner. And this turns out to be a decent estimate, and the complexity goes down from n to the fourth to n squared, and it saves you a whole lot of work. And it turns out that it's very rare that the two numbers are significantly different. So this is the thing that is that we want to minimize. And the question is, what kinds of patterns would you expect to minimize that measure? We have these at least three candidates here of random, quasi-random, and non-random, and it's not immediately obvious which is the best choice. So where did all this stuff come from? It's roughly a century old as a mathematical question. It had roots in ergodic theory and dynamical systems, and the question of if you have a system that can move through many states, will it pass through all of them, or will it be confined to some subspace? And there are also questions in number theory that led to the same kinds of questions. And the focus within the mathematical community was on this question of, can you fill the unit interval? You just take 0 to 1. Can you find a way to put points there that will be equitably distributed, where again, if you then subdivide it into pieces, that you'll find the same number of points in each piece. And in one sense, you really can't do better than just a ruler with a picket fence with points that are equally separated. But that's not the total answer, because what the mathematicians wanted to know was, if you view this as a process in which you're going to add points over and over, and indeed infinitely often, and you want to maintain low discrepancy or high uniformity throughout that process, then where do you put the points in each instant? If you started out just filling this up from left to right, then that wouldn't do very well at all. So you need some kind of algorithm for putting them down that preserves this property of uniformity as the set is being built. So Vail had an idea that turns out to be kind of unbeatable in the mathematical sense, which is if you just take an irrational number, and any one will do, you multiply by successive integers, and each time you take just the fractional part. Say you use pi, and so the first number in the series is 0.141, whatever. Then you multiply that by 2, and you continue. It turns out he was able to prove that this is as uniformly distributed as anything can be in the limit when you get to infinite number of numbers. And this actually turned out to have important practical consequences, because the proof that he used, which had to do with these Riemann integrals, where the Riemann integration process is also using uniformly distributed sampling points. This had a whole lot to do with the origin of the Monte Carlo method that has, become very practically important today. So this is in some sense like the right way to do this. If you want to generate a truly uniform sequence, you take an irrational number and you multiply by a bunch of integers and take the fractional part. The trouble with that, of course, is that when you've got one of these machines, they don't actually do irrational numbers. They do approximations to irrational numbers, and you kind of lose the whole game when you do that. So this is mathematically wonderful. It's computationally not so great. So some other guys came up, not just guys actually, came up with methods that are extremely odd, but very useful and kind of surprising in their oddness. The one that I have been using as an example, the quasi-random numbers you've seen so far, come from Johannes van der Kooput, a method that he devised. And he was actually coming at it from a slightly different angle than Vail. He was trying to put a bound on how much discrepancy a sequence of numbers had to have. And he was asking, 0 is probably not possible, but maybe there's some finite amount that you can create a sequence that no matter how long you make it will never exceed that bound. It turns out it's not so. You can't have a constant bound. The proof of this came in the 40s from Tatiana Pavlovna van Aarden-Ehrenfest, who is a wonderful character if you've never run into her. She's the daughter of Paul Ehrenfest, the physicist, who was a really good mathematician, very sharp, well-respected, never had a chance at an academic position in her entire life. But she did this proof, which many others had been hammering away at without success. There were better proofs later and extensions of this idea. But what this means, what van der Kooput's theorem means, is that this is not a game we can really win. We can only approximate. We can hope to do well, but there's not going to be a perfect quasi-random sequence. So all that stuff was very mathematical, not aimed at any particular use. But while it was going on, this von Neumann and Ulam and the whole gang at Los Alamos were inventing computational methods for Monte Carlo studies. And this idea of doing quasi-Monte Carlo studies actually goes back almost to the beginning. I mean, the first real attempt was in 1947, the first real attempt at Monte Carlo with pseudo-random numbers. And it really got working around 1949. And just 2 years later, this guy Richtmeier, who was the head of the theory division at the time, I think Ulam's successor, decided he'd read about quasi-random sequences, decided it sounded like worth trying because they do have lower discrepancy than pseudo-random sequences. And he was using it for the big problem that the Monte Carlo technique was invented for, which had to do with making nuclear weapons, of trying to trace the fate of neutrons as they bounce around inside a bomb. It didn't work. It worked. It worked no better than the pseudo-random techniques. And one result of this was that it sort of got buried for decades. I am pleased to say that in spite of the fact that he had nothing positive to report, he did publish his experiment, and that I think this is to be encouraged because we wouldn't know about it now if he had just kept it to himself because it didn't give the result he wanted. And the rest is history. So how do we make these things, these quasi-random numbers? This is where it gets really kind of grody. This is how van der Korpitz numbers are made. You start with a set of integers, you write them in binary, and then you use those, you use the integers themselves, in this case for the x-axis. We're using integers 0 through 7. You divide by 8, and that gives you the position of successive dots here along the x-axis. We go 1/8, 1/4, 3/8, and so on. And all the randomness, if you can call it that, that's present here is in the vertical position of these dots. And the procedure for generating those is too weird for words. What you do is you take the binary representation of that integer, you reverse the digits, and then you interpret it as a binary fraction, which is, this isn't even mathematics. This is just playing with digit streams. But it produces something that is a recognizable pattern and yet is patternless in the sense of unbiasedness, and does much better than true random ones. I find that procedure, it's almost offensive. I mean, it is conflating realms of thought that should be kept at arm's length. I mean, on the one hand, you have this arithmetical procedure of dividing a number, 1/8, 2/8, 3/8, which is fine. On the other hand, you've got this thing where you're not actually working with the numbers at all, not numbers in the sense that the Greeks would recognize them. They are just strings of bits or digits, and you're twiddling with them. And the idea that this is actually a well-defined and useful procedure is, to me, just very strange. But there it is, and it turns out that all of the methods, there are a lot of other algorithms. This one's from the Russian mathematician I.M. Sobol. And it's interesting. I'm not going to go into the details of how this is done. It's a sort of gray code where you're changing one bit at a time. But this one has distinctive symmetries to it. And also another thing that's distinctive in all of these things is that you might intuitively guess that uniformity means that the dots are all pretty much the same distance apart. And that's not so. It turns out that the highest uniformity, the lowest discrepancy, comes always with these pairs of points that are actually quite close together. And also some, some gaps that look larger than the rest. I wouldn't have guessed it. So when we apply this to Monte Carlo studies, and I should say I'm specifically talking about these integration schemes, the integration by darts business, where you're trying to essentially measure an area or a volume by sampling. What everybody cares about, what everybody's interested in, is how fast does it converge, or how many points do you need to achieve a certain amount of accuracy, how many samples. And the answer to that question is well known and easy to establish for pseudo-random numbers. The error is going to be essentially the square root of n over n. The convergence rate is square root of n, which is not terrible, but not great. It means that, if you want to significantly improve your result, you're going to need a whole lot more points, and every one costs you something. In Quasi-Monte Carlo, it's a little bit less intuitive and obvious. The convergence rate turns out to be, whoops, I'm doing that again. Turns out to be log n raised to the dth power over n, which is, d is the number of spatial dimensions in the problem. And this, at first looks great because log n is much smaller than square root of n. It sounds like you've really struck it rich here. Log n is, log of a million is only 20. Square root of a million is 1,000, so that's a big factor. But you can't forget about that exponent d there. And that means that we have here a terrific procedure for low-dimensional problems, which is great, except that low-dimensional problems are not much interest, and they're pretty easy. It's the high-dimensional ones that we really care about. And this is the phrase, the curse of dimensionality, is Richard Bellman's slogan, in which he points out that in high-dimensional spaces, things just disappear. Oh dear, I'm running out of time. If you're looking to find a cube in a space of, say, 20 dimensions, a cube whose side length is 1/2 of this larger cube, in 20 dimensions, it's only going to occupy 1/millionth of the volume. So you really have to pour a whole lot of samples in there even to detect its presence. There's another issue that comes up, which is simply that you can't measure the error very easily with Quasi-Monte Carlo. But since I'm running out of time, I'm going to quickly move on. By the 80s and early 90s, Quasi-Monte Carlo had just about disappeared. Quasi-random sequences were still of interest in mathematics, but nobody was using this technique in physics or any place else, as far as I know. And then something happened. Wall Street discovered Quasi-Monte Carlo. And I mean, this is one of those cases where there was an identifiable event. Goldman Sachs wanted wanted some help evaluating these derivatives, financial derivatives that they were selling. And they went to Joseph Traub and his students at Columbia, who I guess on a lark, sort of, they knew that this was not supposed to work, but they tried it anyway, and it did work. They were getting results better than the standard pseudo-random Monte Carlo, and they were doing it faster. Not sure how easily you can see this, but the solid line is their Quasi-Monte Carlo result. And it's very stable and on what we assume is the correct solution from way back here. And all of these other conventional Monte Carlo results are still trying to converge on the right answer. So this made a big impression. It also perhaps had some part in the unpleasantness that followed in 2008 and 2009 when all of those collateralized mortgage obligations turned out to be worth not what they were sold for. I don't really want to blame the Columbia group for any of that. I think their algorithm was correct. The assumptions behind the valuation maybe not so great. The question then is, how did that happen? How did it work? The high dimensionality of the problem is still there. It's not magic. You can't actually evaluate a 360-dimensional integral this way. I'm out of time, so let me just say the current thinking on this is that, in fact, it's not a 360-dimensional integral, that most of the information lies within a much smaller group of dimensions, and that this is therefore rather like this process of compressed sensing where you can tremendously undersample something and nonetheless get to the truth. The Quasi-Monte Carlo process is doing something similar. What's not so clear is how it does it, to what extent it can be relied on to do it, how broad a spectrum of problems it might be applied to. So I'm going to call it quits right there. If there's time for questions, I'm happy to receive them.
We have time for questions.
Oh, okay.
We have time for many questions. Can you repeat the next 5 slides? No.
Brian, that motivating question of the leaf area.
Yes.
You claimed that U-random or pseudo-random is no better than ordered for that task.
Yes.
But doesn't that depend on the shape of the thing you're measuring?
Yes.
Okay.
You can. This is the adversarial issue. You can always invent something. I mean, you could invent some sort of comb-like or fractal pattern that would miss all the points, or that would hit all the points.
But in a non-adversarial spirit, if you don't know the shape of the object you want to measure, let's say you want to make a area estimating widget or anything.
Yes.
It is the case, it seems, that ordered sampling is more sensitive to shape. And that's just the universe.
Yeah, I mean, it depends on the shape.
Well, that's the point.
Yeah, right.
So anyway, it seems like maybe pseudo-random does have an edge.
If you're talking about things that you can clearly formulate in a well-stated mathematical way, you know, if you could, for example, define a distribution of shapes that you're going to be choosing from, we could, you know, you could answer that question one way or the other. In the absence of that, they're indistinguishable. I mean, the convergence rate in both of those cases is square root of n. So it's, you know, as defined, they are not distinguishable. Yes?
I have two really short questions, if that's okay. First one is, when you're using pseudo-random numbers and you're picking random points on a sphere, you have to be super careful, because if you don't do it in the right way, you end up clustering at the poles.
Yes.
Does that same property extend to quasi-random?
Well, the quick answer is I don't know. You know, the trick with picking points on spheres is how you project. That, I'm guessing, you could use the same procedure with quasi-random numbers. Here I go again, quasi-random numbers. Use the same method that works for pseudo-random numbers. I've never actually thought about it, and I haven't seen anything published on it. There is a lot on toroidal forms, you know, and, you know, simple kind of torus where you're just connecting the edges of a square, basically. And this turns out to be a different problem. That is, the solution, the optimal solutions are not the same as they are when you have actual boundary conditions. But it's also not going to be the same as it would be on a sphere. It's an easier problem in a torus than on a sphere, or at least it is for random points. So I don't really know. It's an interesting issue. And, points on spheres are tough.
My second quick question was, so I've actually done some messing about with quasi-random in some Monte Carlo I've done. And I've found it advised a lot of places, if you use Halton and less extent Sobel, you should actually discard the first sort of n points in the series. Could you possibly comment on the thinking behind that?
I think this depends largely on what you're doing with them. I stuck to this integration problem, multidimensional integrals, which is easier and also more clearly well suited to this technique than if you're looking at, say, random walks, or anything where correlations become troublesome. And, you know, random walk is the classic example of that, but there are others. If you were doing like the Ising model or something like that, it's a real issue. And I haven't found a whole lot of literature on, you know, on either applying quasi-random numbers to those applications, nor on this, you know, this warm-up issue that you're talking about, of, you know, warming up the random number generator before you start using the values. I frankly don't understand it, which is not to say that that is why there would be a benefit to that. It's a totally deterministic sequence. I don't understand it, but that's not to say that there isn't something there. It's just that, you know, who am I?
So you said that true randomness has an advantage in the face of adversity. How about cost or economy? That in nature or engineering, if you need to store or communicate a pattern of this, then if you compress it, you pay less. So is that a special case of adversity, or is it another?
I'm not sure I understand the question.
So if I'm paying for sending messages,
yes.
right,
Okay.
I would compress them,
Yes.
and they would not be distinguishable from random.
It's distinguishable depends on what tools are being used to distinguish. They will look random. That is, they'll have the statistical properties of a random sequence. But if it's a lossless compression algorithm, if you know the algorithm, they're easily recovered. So it's
well, but in nature, you don't know, you cannot read the book, right? But still, evolution tends to compress the signals.
Yes, I'm afraid I just don't have. There's a large body of work on which sort of the opposite problem of taking a small amount of true randomness and stretching it out like taffy to distribute it through a much longer sequence and basically get as much bang for the buck as you possibly can. And that's, this is high technology at this point. I mean, cryptography depends on doing that, and there are very clever ways of going about it. But, when you compress something, yes, it looks more random in the sense that the bit patterns are suddenly, they don't have the regularities that you might see, but they're not actually random. They're, it came from a well-ordered, well-known file to begin with, and all of that information is still there. It's yeah. Just one more? Yes. Okay. Yes.
First, thank you for your wonderful talk.
Thank you.
I'm from electrical engineering department, so I'm more interested in the application aspect of Monte Carlo because I'm running Monte Carlo simulations on some circuits to characterize its resilience to process variation.
Yes.
So my question is, I think most of the simulation software nowadays are using pseudo Monte Carlo, right?
Yes. Yes.
And I need to choose a seed each time.
Yes.
I think the advantage of that is I can replicate the result, because if I choose a seed, I can replicate it.
Yes.
But the problem is the conversion rate is too slow. So it's really time consuming for me to simulate it. So I think from your talk, I think the Quasi-Monte Carlo might be a better choice. Do you think it's
as I said a moment ago, it's not being widely used for applications of that kind. I don't think that the mathematical foundation is yet there, that we understand, for example, what errors are possible in that kind of application. But it's ripe for exploration, Give it a try.
Right. There are other methods to converge faster. You can use Hamiltonian or any affine transform, parallel tempering. There's all these other techniques to converge faster with the pseudo-Monte Carlo.
Yes.
So you should explore that before you go into quasi.
Fair enough. Yes.
You should invite her to your talk. There are a lot of other techniques to fasten the convergence rate.
Yes.
Of course, it's called AM27. It covers all these methods, and you learn a lot. Every Tuesday and Thursday, 11:30 to 1:30.
Now a message from our sponsor.
All right, let's take Brian again.